In about a minute I'll show an alternative way, and that will be adding these vectors graphically with an applet. But before I do that, let me just show you what the results would be. After all, it's an odd-numbered problem that you can find in a book. So according to this one here, it says negative the pulling force, which is 80.0 newtons, times the cosine of 30.0 degrees. Before I execute that, I'm going to check if I'm in degrees. I'm not, so I'm going to switch that to degrees. Okay, so the frictional force is negative 69.3 newtons, and it should be negative because it's pointing to the left. That's what you saw earlier in the other recording emerging from the algebra. Now the other equation here for the normal force is going to be negative 80.0 times the sine of 30 degrees minus the minus negative 196 newtons. As you see from the algebra, it says minus the weight, but the weight already is a negative, so that's why I say minus negative. And I come up with 156 newtons for the normal force, which is positive and therefore points upwards. And then over here with this little equation, you determine the coefficient of kinetic friction as being negative the frictional force, which is itself already is a negative, so negative and negative make a positive. Getting rid of that, so I'm going to have 69.28 rounded divide by 156 for the normal force, and I come out with 0.444, and that's also what you find in the back of the book as the answer to this problem. Okay, now here's the alternative way. This website here from the University of Calgary I've posted in several places, so you should be able to relatively easily find it. I'm going to move this out of the way because I need some more space here. 4 vectors are involved, so I'm going to add a couple of vectors here. These are totally out of whack at this point, but here's the first one, the 80 newtons at an angle of 30 degrees. I just hit enter. Then I'm going to have 196 newtons. That's the weight. 20 times 9.80. That's 196. At an angle of 270 degrees, so it points straight down. Again, I hit enter. That's what the applet requires every time I put in new numbers. Hit enter. Then I'm going to put the normal force in, which at this point here, in order to work the applet, I'm going to put at 0 for now. And I'll explain it in a moment. At 90 degrees. Again, I hit enter. And then the friction here is 0 at 180 degrees to begin with. The friction and the normal force, I don't know them. I'm just going to keep them at 0. Overall, of course, it says that the velocity is constant, therefore the acceleration is 0, therefore the net force is also 0. So when I compute the resultant, that green arrow here, that should come out to 0. Of course, it doesn't at this point because I only have the pulling force in and the weight. So I have to adjust the normal force and the frictional force in order to come up with something that is as close to 0 here as possible. I'm going to start with the normal force and just put a value in here. It should be less than 196 of the weight, as the weight is pulling down. The pulling force is pulling a little bit up, so to the vertical component I should add the normal force, so I'm going to just guess here at 150 newtons. And oops, that was the wrong entry here. This is still 196. This is what I meant to do. 150 newtons here. And now I'm going to show the resultant, and almost there. I'd like to get this at 0 degrees at this point here. That's also why I start out with a 0 here and a 0 there, so I can adjust one after the other. Okay, so 150, I think I need a little bit more, so I'm going to try 160. Okay, let's see what I get. Apparently I always have to click on the show result, and now I'm at 3 degrees, so I'm going to go in the middle here, 155. And this is pretty close to 0 degrees here, maybe 156. Let's try that. Oh, right on. 156 newtons is the normal force. So that's the blue one that you see behind that pink. I'm sorry, it's the pink one that you see in front of the blue one. Now I need the frictional force, which points to the left. I'm guessing somewhere around less than 80, so I'm just going to guess here 60 for now. And pretty close here. I need to get this down here to 0. Notice the angle is still virtually 0 degrees. So a little bit more. Let's try 70. Okay, that points in the opposite direction, so a little bit too much, so I'm going to try 69. Let's see what we get. Point to 8 here. 68. 1.28. So 69 is probably the closest one that I can get. And you can see that I have virtually 0 newtons here for the resultant. And with this kind of trial and error here, I came up with 69 newton for the frictional force. And when we compare that with what I calculated earlier, yep, that's what it says, 69, negative 69 for the frictional force. And here, of course, it says 69 newtons at an angle of 180, which is to the left. And for the normal force, 156 pointing up. And that's what it says here, 156 pointing up. And then, of course, when I type in these numbers again, I'm going to have 69 divided by 156, which is, except for the last significant figure, the same, 0.442 in this case. And because it's a little bit of trial error method here, you come up with one less significant figure, but that's okay. And mainly because this one here is only 2 significant figures. Okay, so that's the alternative way. Do it the graphical way. And that applies to quite a few other problems as well that you may encounter in this chapter.